Hello, welcome back. This is Matthias speaking. I'm going to present the KLayout workshop, part 4. Part 4 is the part we were not able to give in Villach on-site because of time reasons, and I'm going to present this now in a form of recording. We will be lacking the hands-on experience, but I hope I can compensate by explaining the examples and exercises in more detail. As a reminder, these were the parts we have been given already in Villach. So the first 3 parts were about how to read layout, how to draw layout, and how to turn a design into a layout. And we will come now to the secrets. Actually, we are not talking really about secrets because what I'm going to tell you is pretty well documented and publicly available on the internet. There are many resources about the topics we are talking about. First of all, there is the forum, which is the community. There are many people able and willing to help you, including me. There is GitHub, the GitHub project with the source code and also an issue tracker and some discussions going on there. There is the documentation page. The link points to some introduction. There is the API reference, which is not easy to understand if you don't have any introduction. However, I think it's quite useful once you are experienced enough. And last but not least, there is the KLayout Python module, which is a standalone module, which basically includes most parts of the KLayout API. And we will talk about how this relates to actual KLayout itself. And as another reminder, we were using KLayout, we were using the Sky130A elements package, and I was also showing you some sample layouts. At least you will need KLayout and the Sky130A elements package because it includes the examples we are going to deal with here. Now let's start with the fourth part. Layout scripting, in general, is a way to generate layouts in an algorithmic fashion rather than painting it yourself. What we are talking here is the lowest level of scripting of layout, and it's quite useful, as I said, for devices. It's also useful for generating gates. It is also useful for pattern, for example, regular structures varying certain parameters of a layout. And you need this kind of pattern, for example, to develop a process and to assess the quality and the boundary conditions under which your litho process will work. In general, layout generators can be wrapped into p-cells. So a layout generator, first of all, is quite simply a function that creates polygons or other geometric objects based on a number of input parameters, which are, in the case of a MOSFET, for example, width and length and maybe number of fingers. A p-cell is essentially a wrap around this. It is a way to declare the parameters in a way they can be presented by a user interface. And the advantage is that you have a kind of visual integration. The p-cell will be available to the system for the library manager in a sense of a normal cell. And you can place it in your layout and configure it. And you can change the parameters and it will automatically adjust. Technically, it's always a single function that is called, which you can provide and where you can put in all the logic of your layout generation. So as I said, potential applications for KLayout scripting is the generation of layout, but you can also manipulate layout, for example, delete layers or transform layout or manipulating the hierarchy. You can analyze layout. You can create add-ons to the application. So there is an API able to provide user interfaces through the binding of Qt classes, and you can plug in new dialogues, for example, into the menu, and hence extend the application with new dialogues and new menus. And it's also possible to implement new channels for I/O. So, for example, to implement new readers for particular file formats. You can also implement, for example, machine interfaces like to control a microscope through KLayout. There's some legal stuff that matters, which is related to the license chosen for KLayout. KLayout itself is published under the GNU public license. The GNU public license is a not quite permissive license. It's a little bit restricted. And it means when you take the source code of KLayout and you modify it and you publish it yourself, then you have to publish the resulting system again under GPL. So this is called the copyleft principle, and derived work needs to be published under GPL. The open question here is what happens if you run a script inside KLayout. The question is whether a script will also count as derived work. Technically, a script will call functions from inside KLayout, and this does mean that the code of your script will not work without KLayout. In that sense, a script and KLayout are bundled and could be seen as derived work, but my interpretation, and this is clearly stated in the license requirements, is that scripts do not count as derived work, so you're essentially free to code any kind of script, any proprietary one, and you don't need, if you want to publish it, you don't need to publish it under the GNU public license. So you can even sell scripts running in KLayout. The GPL obligations only apply if you extend the C++ core of KLayout. KLayout comes with some runtime options. First of all, it offers a choice of 2 languages. So first it offers Ruby, second it offers Python. Ruby is a language that was very popular like 20 years ago, or still is popular. Python today is more popular. Both languages are not quite different, so it's probably easy to switch between both. If you prefer Python, then please use Python to code your scripts. In my examples, I will always use Python. For example, Ruby is used in the DRC framework, and hence DRC scripts are coded in Ruby. You should be a bit familiar with Ruby, but as I said, it's not very, very difficult to make the transition from Python to Ruby and back. In addition to the integrated Python, there's also a standalone Python module that you can install using pip. The pip module is really called KLayout. So you see on the left side at the bottom how you essentially import layout. So you import KLayout and then a submodule, and the submodule is DB, for example, for the geometrical engine. And there are also other submodules like LAY, which is the visual part. This Python module does not come with user interface integration because it doesn't link against the Qt framework. It just comes with very basic functions like screenshot ability and things like that. So it can be used in environments where you want to generate pictures, but it cannot generate user interfaces. On the other hand, on the left side, you see how Python inside KLayout is used. So the module here is called PyYA. In the future, this will change. And KLayout will also support klayout.db, etc. So you can use the same scripts within KLayout and also outside KLayout. The KLayout macro IDE is an integrated development environment. You can basically use your own IDE like PyCharm and configure KLayout as a Python interpreter. However, this means when you run a Python script from PyCharm, this means KLayout will start again and you have to reload a layout file, for example. So you have to set up everything and then the Python script will execute. On the other hand, if you want to leave your layout loaded and want to run Python scripts, then you have to do so from within the environment. And it's not quite as powerful as PyCharm, but it has nice features such as a debugger and syntax highlighting and things like that. So I think for daily use, it's good enough. Maybe if you write large packages, then maybe you would rather switch to PyCharm or any better IDE. I think it's time to start a demonstration. So this is KLayout as we see it when we freshly install it. The first thing I'm going to do is I'm going to install the packages, specifically the Sky 130A elements package. So I go to Tools, Package Manager, search for Sky 130A, double click, click Apply. I have to confirm. Then it's fetching the files. Then it asks me whether to run scripts. Let's choose yes, and once again for the X section package, and that's it. So close. Now we should see the Sky 130A technology here. Second thing I'm going to do a bit of configuration. So we have the usual environment in terms of background and so on. So let's pick a black background. Let's choose color for the decoration stuff, be a bit lighter. Let's make the axis visibles, set it to lines. So, and now we should be set up more or less in a way. that is useful for this Chi-130 technology. And to use the macro development IDE, you go to macros, macro development. So, and you see here, so this is the macro development IDE, and it consists of a basic tree of macros or scripts. It consists of an editing panel with multiple tabs and of a console. And the console is easy to use, so you can choose one of the languages. So let's pick Python. You can type any command and hit return to execute it. So in order to create a script, I need to tell the system where to generate the script. I have a number of branches. Some of them are read-only, so I cannot create scripts there. And in my case, I have two places to create scripts. So one place is called Python branch. This is intended for Python modules, so Python scripts that I can include from other scripts. Local means a place inside my home folder where KLayout stores its macros, unless I place it somewhere else. And this is the place I'm going to create my script in. So let's hit new. And now I get a selection, a choice of multiple templates. I will select the first one. It's a file called lym, which is a generic macro type. And it's actually an XML format, and it allows me to store additional information along with the macro text. For example, to indicate that the macro is supposed to appear somewhere in the menus. So, and now I can enter some text. First, I should rename this script to first, for example, and let's put in some macro text. So simple print function. And now for executing it, I have two options. So one is that one, and this is the other one. This is the run current script. So one of the scripts I have loaded is the current one. Run current will load this particular script and run it. And this button is the run this button, which runs the current tab I'm in. This only applies to cases where I have multiple tabs or multiple scripts loaded. In that case, it doesn't matter what I take, and I just pick that one. And then it reminds me to save my script. It's not strictly required, but in this case, it's helpful. So, and it will print 3, which is the output of that statement. And to show you a more elaborate example, for example, I can open a message box. Okay. So this is a built-in function of KLayout, or more specifically a class, and it will open a message box. Let's try that one. So again, I'm reminded to save it, and then this message box appears here with the title and the text I have indicated in a single OK button, because I configured it to have only one OK button. And with such a macro, I can bind this macro to a menu. So I hit this macro properties button here, which is the middle one from there. And I can give some description, my first macro, for example. And I can say show in menu. If I leave the other entries empty, then it will choose a default location. I will hit OK. And then I can close the macro IDE, because now I find my macro here under macros. And this is the description I gave it. And when I click this menu item, this script is executed and the message box pops up. So this is a very simple way to add scripts or new features to your menus, and to run your custom scripts, which can do any kind of things, like also providing new features that you don't find in KLayout per se. Okay, so this is the macro IDE. The macro IDE offers more things, for example, a debugger. So in order to run a script under debugger control, I can generate or can set a breakpoint here. So I click here, I have created a breakpoint. Now if I run the script once again, so now I use one current script, then okay, again, I'm reminded to save it. And here you see it stops now. Now the background turned red, which means it's in breakpoint stop mode. And while it is in breakpoint mode, I can essentially use the console. And I also have a list of current variables, local variables, which is essentially pretty empty here, except a few things. And yeah, if I had a longer script, I could use the step through buttons here to either step into procedures or to step over procedures. This button will stop the script execution immediately. I can set new breakpoints or clear existing breakpoints. I will now just, let's just continue. Step over here. Now you see the script is running, so the background is green, which means script is running and the info box is shown, and if I hit OK, the script will terminate because this is the last statement of the script. Let's continue with the presentation. So first of all, we are going to talk about layout generation. And the first example I will show you is a simple generation of a single rectangle. So here you see the output that we are supposed to see later. And here is the script which generates this output. So let's briefly walk through the script. So first thing that happens, apart from the import, is we create a layout object. A layout object is essentially representing a GDS file. You can load a GDS file into a layout object, but you can also write a layout object to a GDS file. Initially, the layout object is empty. And an important property of the layout object is the database unit, which is needed because GDS stores geometry as integer coordinates. So this means the coordinates are stored as integer multiples of the database unit. And by default, the database unit is a single nanometer, which means that you can only create geometries in increments of nanometers. But you can also set the database unit to a lower value. Next step is we will create a layer inside the layout object. So the layer here is given by a layer and data type number, but it can also be an anonymous layer. So for being used as a temporary layer. And layers are always shared among all cells. And the return value is a layer handle. It's technically an integer value which identifies the layer inside the layout. Next thing is every layout needs to have at least one cell. So we create one and we call it top. And the return value of this function is a cell object. But be careful, the cell object is not like a typical Python object. So for example, you cannot move it around and insert it into a different layout. Instead, it's a kind of pointer that points into a specialized structure in the layout. And the next thing is I am going to create a box, a rectangle, and it takes 4 coordinates. So this is the left, bottom, right, top coordinate. And it's important to know that the box type here I am using is a particular one that allows me to specify the coordinates in micrometer units. This is indicated by the capital D. There is a box without the capital D. It takes integer units, and there's a box with the capital D, and it takes micrometer units. If I use the D box, I can specify coordinates in micrometers. This is a convention. The D box basically is simply a box that has floating point coordinates. But within KLayout and in the functions that will follow, the convention is that a dbox object is given in micrometer units, while a box object is given in database units. And finally, this is how I insert the box into a layout. I take the cell I want to insert the box into. I'm obtaining the shapes container for a particular layer. So a cell is essentially a collection of shape containers, one container per layer. And in this container, I insert my box. And after inserting, the box is essentially detached. So what it does, it will insert the box into the cell and keep an internal copy. So when I modify the box later on, this will not have any effect on the box being stored inside the layout. So after this operation, I can essentially discard the box object. And finally, the layout is written to a GDS file. Let's try that. So I have prepared a number of samples, and these samples are found inside the Sky130A element in a special folder that is not visible as of now. You cannot just load a file from anywhere inside the macro IDE. So what we are going to do is we are going to add a location and tell it to look for files there. And in this particular case, the location is here. Because I'm on Linux, and salt Sky130AL in samples, scripts, Python. Okay, so let's add this location, and you see I have a new entry here, that one, and it points to this location, and below this location I find the examples. And first thing what we're going to do is look at the sample 1. So I double click it, I have opened it, and this is exactly the text you have seen before. Let's put in a breakpoint and start it, just to show you how execution happens in the debugger. I use this button because I want to run the new sample I've loaded. I use the run this button. So now it starts, now it stops at the breakpoint. Let's step over. So this is the step over function. And now you see I have a layer 1 variable, and this layer 1 variable has the value 0 because I have generated the first layer with index 0. And you use it later in the insert functions and other functions. Next thing is step over the cell generation, and then I see I have a cell object, and the cell object has a number of properties, specifically the name and some other properties that are not important now. And now it basically has inserted the box, and now the script finished, and it should have written a GDS file. So the question now is, where is this GDS file? I haven't given it a path, which means it's written to the place where I've started KLayout from. This is not quite clean, so if you want to be sure to know where the layout actually ends up, it's good to give it a path. I know that I have started KLayout in my home folder. We should see a file there that is called sample.gds, and it has a single rectangle. So this is the file we just generated. Okay, this is the first example. Let's go to the next one. Second example is about creating cell instances. So the goal is here to create a number of instances of cells. We will see how this actually looks like, that these are real instances. And this example also will show you how you generate a cell array. A cell array is not a single instance, but an instance made from regular placements of a single cell. In this case, we create a 3x2 array, and the array is specified by a dimension count. So in that case, in that direction, it's 3. In that direction, it's 2. And 2 vectors that specify the axis where the dimension advances in. So there's one vector pointing from here to here, which is in this case the A vector, and it's 0 in x and 3 in y. So this is this step. And we have a second vector going from here to here, which is the B step. And this is 4 in x and 0 in y. Both are micrometer values. So, and coming to the script. So everything else before is already known. It's like what we discussed before. Now we see something that is a very important concept inside KLayout. it is the concept of transformations. A transformation is an object that describes a displacement, a rotation, and a mirroring operation. In this case, we have simple transformations, so that means the rotation is confined to multiples of 90 degrees. This is a subset of the affine 2D transformations, and here I use the star operator, which means multiplication, and essentially it boils down to a matrix multiplication, but intuitively it means apply the second transformation before the first. In effect, it computes a combined transformation object, and what I want to achieve here is I want to rotate my cell and displace it by a specific vector. And this gives me the first instance, so the lower left one here. So this is the placement of that cell instance. The cell itself will have the same rectangle than before, but now we have rotated it, so it's kind of flat. And it's placed at this position, or rather the center is placed at this position. So this should be 1 in X and 2 in Y direction. And also the cell is rotated. And in addition, I will generate a vector or an array instance. And here you see how the arrays are built. This is the formation formula for the array. So I have two indices running from 0 to NA -1 and 0 to NB -1. And this is multiplied with the A and B vectors, and this gives me my displacement. And this generation function is essentially generating my array. And the object I'm using here is dCellInstArray. Actually, array is always used. So even if it's a single instance, the object I'm using is called dCellInstArray. And for a single instance, I just skip the last 4 parameters. And the reason it's called array is simply that it is always a kind of array, and the single instance is just a special case. And I'm using a dCellInstArray, which means the values I'm entering here are all micrometer coordinates. And finally, I insert this instance array into the top cell. So this time it's not a shape, it is an instance, which means it will place the child cell inside the top cell. And the result is the one we have seen. And let's see this in action. So I will open the macro IDE once again. Let's open the second example. This is exactly the text we were looking at right now. So let's call 1. And now you see it offers me to reload the file because we called the output file sample.gds like before. It has overwritten the file, and now it offers me to reload it. So let's push reload, and we have to zoom in a little or zoom out. And you see 6 instances of the child cell. And when I increase the hierarchy level, I also see that the child cells are made from a single rectangle. And you see this small tree here. So I have a top cell and a child cell, and the child cell looks like this, and the top cell has 6 instances of this child cell. And by the way, this also shows that a single instance is capable of generating a large number of child instances through arrays, and technically this can be millions or even billions of child cell instances with a single object, just by using a high number of NA and NB. Let's get back to the presentation. I finally want to explain in the third example the region object. The region object is technically a collection of polygons, and we will use it to generate a 3-colored picture here, or 3 layers in effect. And what we are going to do here is the following. So first we generate a rectangle, or a square in this case. So this is the thing that has the green outline here. Then we are going to rotate it by 45 degrees. And then we are going to take the difference. So we are subtracting the reddish shape or the red outline from the green one. We do the opposite. We subtract the green from the red one. And then we create the intersection of both, generating this bluish octagon here. And the script is essentially simple. So first of all, we have to generate 3 layers. we have to generate again a top cell, and now we are producing the region. The region is an object that is basically a standalone collection of polygons. Unfortunately, the region does not offer a D version, so we only can use database units here. So first thing we are going to do, we are going to insert a box, and this is a square, so it starts with -500 database units. Since we haven't changed the database units, it's still nanometer, and the lower left and lower, and so the lower left coordinate is -500 -500 nanometer, so half a micrometer, and the top right coordinate is 500 nanometer, so half a micrometer, and this makes the box a 1 by 1 micrometer centered box. Next thing is I'm going to transform the box, and as we want to have a 45-degree rotation, we have to use a complex transformation. So complex transformations are extensions of the simple transformations, and then they allow me to specify a scaling. In this case, it's 1. So we don't want to scale an arbitrary rotation angle in degree. So in this case, we are using 45 degree. This is the mirroring flag. So we don't mirror. And this is the displacement, and the displacement is 0. So we don't shift. And the I complex transformation indicates that I'm converting integer units to integer units. The complex transformation can also convert types. So it can convert floating point values to integers and vice versa. And this is useful in connection with the scaling feature to, for example, convert between database unit space to micrometer space, as a side note. So here we are just creating a complex transformation implementing the rotation. I use the transformed function, which takes the region, applies this transformation, and returns the transformed copy. And then I compute the difference. So the minus is the geometrical difference. So it will take all the shapes from R and subtract all the places where RT is present, so the rotated square. And we do the opposite, so we subtract R from RT, and then we compute the intersection, which is indicated by the end. So this is a Boolean not, and this is a Boolean and. And then we insert these 3 regions into the 3 different layers and save the layout. Okay, let's try this again. Open the macro development IDE. Let's open the third sample. Let's run it. So, and now I need to reload again. I have overwritten my sample.gds file. Okay. Let's zoom in. And now you see this is the picture we've seen before with different colors. So I haven't configured the colors. So the third layer is this octagon. The second is the rotated square minus the unrotated one. And the first one is the unrotated square minus the rotated one. Let's get back to the presentation. There is some further reading I can recommend. So first of all, there's KLayout's manual explaining layout database concepts. It also explains the geometrical object concept. And of course, there's a reference with all the class definitions and the various methods available and so on. So then let's come to an exercise. So if that was an on-site training, I would ask you to do it yourself. Now we will walk through the exercise and I will explain you how you actually solve this puzzle. We are going to generate a fractal shape, and the snowflake is generated according to a very simple principle. So you start with a triangle, and then you take an edge of the triangle, and then you divide this edge into 3 parts and substitute the center part by such a wedge. So essentially you split a single edge into 4 edges, 2 of them being connected in this wedge form. And then you repeat this process with all edges that have freshly been created. So you take this edge, this short one, and also substitute it by 4 other edges. And you do the same for all edges. And then you do this over and over again. So in our case, we cannot infinitely nest the line because it would generate an infinite number of shapes. We are going to confine ourselves to 10 levels of nesting, which eventually boils down to almost 4 million individual edges. As a hint, a line can be made from a path. A path is essentially an object that is a line with a certain width, and you can generate a path using that form. So a deep path object, you give it an array of deep point objects and a width. And also you can implement scaling by using the d-complex trans, which is a complex transformation that allows scaling, rotation by arbitrary angle, mirroring, and a translation vector. And this is useful to generate the transformations of the individual pieces. And my suggestion is to implement the thing through a hierarchy. So you can implement it by a recursive algorithm that is also available on Wikipedia, for example. But my proposal is to build the edges from cells and build the cells themselves from subcells. So this essentially means we are not drawing the edges directly, but we are composing them of pieces. And the pieces are cells, and the cells contain other edges or other cells, and only in the final stage, on the leaf cell, we have a real edge. So this shows the principle. So I want to achieve this wedge form here. So, and it's supposed to resolve into that next level fractal shape. And I can do so by placing 4 cells. So cell 1, cell 2, cell 3, cell 4. All the cells are the same, but I will arrange them in a way they form this wedge thing. And if I continue the same scheme down in the subcell and do this over 10 layers of child cells, then I reach this snowflake form if I combine 3 of these things together. The advantage of that is that a cell is essentially a very effective object. And since I use recursion through cell hierarchy, I can generate a huge number of cells with few objects, in fact. So this is the idea behind that. I've also included that in the samples. So it is the snowflake script. Essentially, what we are going to create is a first level cell containing the edges. So here we have again the layout, the layer. We build the first cell, so we call it C0. The names have to be unique. Then we create some constants. This is the first level, and we generate a path for the first level with a width of 10 nanometers. And then we go into a loop, and in every loop we generate a new parent cell, and we produce the placements of the child cell to form this kind of wedge arrangement. In order to form this arrangement, we need 4 instances, and we do so by iterating over an array, and each of these instances, and here we generate the instance, and then we use the current cell as the next child cell and go into the next iteration. And when we are done, we generate a top cell and we produce a 3 cell arrangement forming the triangle and write the whole thing to GDS. So let's start this. Again, we overwrite the sample GDS file. Let's reload. And here you see how the first level looks like. So we are having 12 instances of the C9 cell. And if I increase the hierarchy level, you see the C9 cell resolves into 4 instances of C8. So here. And well, here you see how the hierarchy looks like. So C9 instantiates C8, C8 instantiates C7, and so on. So down to C0. If I increase the hierarchy level, it gets more and more detailed. So like, but we still have some instances here. It resolves further down. And at some point, we start seeing the edges. So the paths that we created. Let's go back to the presentation. In the next step, I want to explain how to build P-cells in libraries. Just a brief explanation. P-cells wrap a function that generates some layout, and it wraps this function into a special object, which also provides definitions for the parameters I want to have. A P-cell is essentially plugged into the system, and it acts as a generator for normal cells. The only difference is that a P-cell can be configured, and if I set a parameter internally, KLayout will build a variant that represents a particular parameter set and then offer this cell for placement. A P-cell also offers other services. So one is to generate a display string that is shown. It also allows you to define a parameter legalization function for example, to enforce limits. You can also define parameter change callbacks that are connected to the user interface. So once someone changes a parameter, you can take some action, and it can also convert a shape into a specific p-cell instance. Usually you use p-cells from inside a library. A library is basically a separate layout object that is registered into KLayout, and if you pull a cell from a library, KLayout creates a link, and when you save your layout to a GDS file, this link is stored in special metadata inside the layout file, and when you load it back, this link is restored. Here is a recipe how to implement a p-cell. I will walk through that quite quickly, so there is more documentation available on the KLayout webpage. Most importantly, what you need to do is you need to define your own class. In this case, it's Circle. You derive from a class that is called p-cell declaration helper. First thing you do is you declare the parameters with a name, with a description, with a type. Here we have 3 parameters. We are going to create a circle, a simple circle p-cell, and it has a layer where to produce the circle. It has a radius and a number of points the circle resolves into. Here we have a function that explains the p-cell, and here is the simple production function that uses sine and cosine to generate the circle as a sequence of points, and then turns it into a polygon and inserts it into the current cell under the given layer. So you see one thing that is quite convenient. So if you declare a parameter called L, it will become available as a class attribute called L as well. And as we have a layer, it's not only available as L, which is essentially the abstract layer definition, so GDS layer and data type, but also as a layer handle, the layer index we were talking about earlier. And then this variable or this parameter is called L underscore layer. So underscore layer is the suffix KLayout will use to indicate the layer ID. And also for the R value is simply available as R attribute. So whenever I use this attribute, I get the current value of R. So, and once I have defined a p-cell, usually want to put it into a library. The way you use a library is you generate your own class derived from PYA library. The library comes with its own layout object. This is where your objects live in, and this is where I register my p-cell. So circle is the class I have defined before. I register it under the circle name. Then I finally register the library in the system under the name simple sample lib here. And in order to get all this up and running, I have to instantiate this object here, mylib, just once, and once this is done, it's registered inside the system and available in the library manager. Let's do an exercise where we can walk through that. So let's generate a spiral p-cell, which is essentially just an extension of my circle sample. In this case, we have 2 radii, and we also have the number of turns, and we want this to become a path, so a line that winds down or up and has a certain width. So the parameters we need is the inner and the outer radius, the width, the number of turns, the layer we want to produce this on, and the number of points per turn. So this is the exercise. Let's switch to our KLayout environment again. Let's open the spiral sample, and this is the fully worked out exercise. So you see here I have also included the original circle p-cell. This is the code we just looked at. And then below I have the spiral implementation, which doesn't look much different from the circle p-cell, except that it has some more parameters here. Of course, a different text here. And then the function to generate the spiral is a little bit different. Namely, it generates a list of points now using n turns. So not just a single turn, but n turns. And then it generates a path instead of a polygon. But otherwise, the code is pretty much the same. And when I register the library, I will register 2 p-cells. So one is the circle p-cell and one is the spiral p-cell. So let's run this code. And now I can basically close the macro environment, and let's see this in action. So I create a new layout. For the initial layer, I use 1. So we have something to play with. Let's zoom out a little. And now inside the library manager, I see this library appearing because that is the one we just registered. This is not persistent. So when I restart KLayout, this library is no longer there unless I restart the script. And if you want to avoid this, there's a nice feature. you can essentially enable auto start for the script. So you do here in the script properties, you can essentially click this button and then the script will automatically start it when KLayout starts. And this means your library will become available again automatically. Let's see the pcell in action. As I said, I have this simple sample up here and it has the circle and the spiral. So let's pick the spiral and I drag and drop over here. Now, first of all, I don't see anything because I haven't selected a layer yet. On the page of the editor options on the pcell page, I have the layer. Let's choose the only one we have available. And now let's pick some outer radius. So we have 1, 2, 3. Let's use a fractional number of turns. So you see now it starts here at angle 0 and then it makes 5.6 turns. And now let's just place it somewhere. Let's go to select mode to stop placing instances. And I have to again increase the number of hierarchy levels to actually see my pcell. And now here you see the path winding 5.5 turns or 5.6 turns. And let's double click here. If I double click, I can edit the parameters and I can change it. Like, for example, I can change the width. So as soon as I leave this edit box, the width will change, or I can change the number of turns. Let's make it 17. Okay, now it's pretty dense. Let's make it 50 nanometers so it doesn't overlap. That is the pcell example. And last but not least, I would like to come to the matter of DRC scripts. DRC scripts, small introduction, they are written in Ruby. Although the main purpose of a DRC script is verification, there are manifold other use cases. For example, you can analyze layout. So for example, measure area, things like this, densities. You can generate new layers, or you can, for example, generate fill features for density leveling. There are manifold options and things you can do with DRC scripts. And essentially, DRC scripts are not something special. Everything you can do with DRC scripts, you can also do with plain Python scripts, but DRC is a bit more compact to write and easier to use. When we talk about DRC, we usually mean the one DRC deck that comes with your PDK. So this is reflecting the formal DRC that is recommended or required for sign-off of your layout. But in KLayout, you can create your own DRC decks for any kind of purpose. So it doesn't need to be related to design manual or any kind of design rules. And this is useful if you want to have ad hoc checks for verifying some assumption you have about the layout, not necessarily meaning you cannot manufacture it, but would like to see, for example, if there are very large patches of metal or things like that. The DRC language is based on Ruby, as I said. So since Ruby is flexible in its syntax, you can create new languages that look like their own language, but in fact are Ruby scripts. This is called a domain-specific language. You see below that if you compare left and right, actually the difference is not quite large. So you don't use colons, but you use end statements to finish a block. The print is called put-as. Brackets are optional, which I personally like a lot. So in the last line, you see you can call a function without needing to add the brackets, which I usually forget. Apart from that, it's pretty comparable. I'd say if you understand Python, I think you also understand the way Ruby works. So a basic DRC flow is usually that you import some shapes from some layers, that you derive new layers by a number of operations, and you output these layers somewhere. So it's either a report database, or you can write it to a layout or to the original layout even. Layers can be different types. So they can be polygons, they can be edges, they can be edge pairs, or they can be texts. But they can never be a mixture. A layer is a type thing, and it will either be polygons or edges or edge pairs. An edge, by the way, is an infinitely thin line connecting 2 points. And an edge pair is a combination of 2 edges, and an edge pair is a useful concept to represent DRC violation markers. The operations supported by DRC are checks, naturally, Boolean operations and not XOR and so on. Sizing operations, it has a number of filters, so filtering polygons by area, edges by length, and so on. I need to say polygons are always meaning, or at least by default, meaning the hull of a set of polygons. So if you have touching polygons, it will always consider the combined polygon and not the individual polygons. Then there are relations, interact, overlap, inside, and so on. So interact, for example, will select a polygon or a group of polygons that touch or overlap with another polygon from a different layer. And there are also conversions between the different types. And DRC has 3 different run modes. So one is flat. It's essentially a very fast mode, but it's quickly prohibitive in terms of memory consumption. So you can use flat mode if you have very small layouts like single standard cells, things like that. There's tiled mode, which essentially walks over the layout in tiles. So it takes a small clip from the layout, works on it, and then proceeds to the next one. This mode is only good if you have already layout input that is not hierarchical. The problem is that it will always produce flat layout. Flat means without taking the hierarchy compaction into account, and this means usually a lot of memory. This is a mode that scales well with the number of CPUs, but on the other hand, since it generates flat layouts, it's usually not a good choice if you have large designs, only in cases where the designs are already flat. Finally, there is the hierarchical mode, also called deep mode, and it tries to make use of cell hierarchy. This is my personal favorite. So I think it's the best compromise between memory consumption and performance. Problem is currently it doesn't scale well with the number of CPUs. So sometimes it can make use of it, sometimes it doesn't. It's still being improved and its work is in progress here. What you need to know about KLayout DRC is that it has instant execution. So this means whenever you have a DRC function, it's executed immediately. And the DRC layers are essentially objects held inside Ruby variables. The advantage of this approach is that you can use loops, for example, and conditions. So you can check whether a layer is empty and take some action depending on the output. On the other hand, the problem is that since layers are kept in variables, they are not necessarily freed because your script doesn't know whether you might need them in the future. Luckily, there is a solution, which means you can call a method called forget, and then the memory will be released, which is often useful because memory tends to pile up otherwise. There's another thing that cannot be done in instant execution mode, which is optimization. So, for example, an operation that is not needed to be executed because one of the inputs is empty, it will still execute because the execution engine cannot optimize away a call. So here you can see some samples. In the first sample, we will send the output to some report. So instead of sending it to an output layer, we will create a report, which then makes the marker browser pop up. Second thing is we will take layout from layer 1, data type 0. We will do a width check, and then we will output the results to the report in the category called 1/0 width smaller than 200 nanometer. This is a simple example for an ad hoc DRC check. On the other side, on the right side, I'm inputting some layer from layer 1 data type 0. I'm oversizing. I produce the difference of both, and then I send the output, in this case, to layer 2, and this gives me the small rim here. Now, our last exercise. This is quite a useful feature, in fact, or quite a useful function. So I think it's worth elaborating a little on it. So the exercise is about finding the smallest feature in my layout, or rather telling me what is the smallest width of a feature inside the layout. And DRC can answer this question by using bisection. So you start with a known upper and lower limit. You take the middle value between both limits. You check whether you see errors when you check the width against the middle value. And if you see errors, this means there are features that are smaller in width than this chosen middle value. And in that case, you set the upper limit to the middle value. Otherwise, you set the lower limit. And then you repeat the process, and you can basically check the emptiness of a layer using this empty predicate with a question mark. And it's also worth noting that internally all dimensions are rounded to the database unit, and this has some implications on the stop criterion, which means here, like I indicated, you should stop before you are below a single database unit, because otherwise you risk ending in an infinite loop. I was choosing 1.5 database units, and I would prefer to use deep mode because it simply has the best performance. So again, I would encourage you to try yourself. but I will show you now how this problem is solved. So let's open the macro IDE once again. I provided this solution also as a DC script inside the package. In order to see it, we have to add the location to the DRC tab. And in my case, the location is in my home.KLayout salt sky130a element. For Windows users, this is not .KLayout, but KLayout. Then it's in sample, no scripts, /DRC. And here I do have the find smallest width. Let's open that. And in this case, let's really pick a good example. Let's close this one. Let's take the Caravelle harness chip. I mean, it's not a really, really big one, but it's like already has a certain complexity. And okay, I will attach the Skywater technology, so I have all the correct layer names here. And this sample is going to take the diffusion layer, so this is our input. And now the script is supposed to tell me what is the smallest feature inside the diffusion layer, and I somehow assume that it's going to be somewhere here in the SM area. So you see 140 nanometer. This appears to be my smallest feature. Let's check what the script will tell us. So we'll open the macro IDE once again. This is actually the script. So it takes some input. This is diffusion here for Sky 130. This is the iteration. So I stop when I'm below 1.5 database units. And it actually computes the center value between the limits. Then it performs the width check, checks whether it's empty. And depending on the output, it will either set the lower value or the higher value. Let's just run it. Again, I use run this. So then it runs a few seconds. And you see here it logs basically the progress. So this is the output from this line. And it prints the resulting width to be 140 nanometer, which is consistent with my observation before. So you see the whole thing took like 2.5 seconds. And given the, well, non-trivial complexity of the input layout, I think that's a pretty noteworthy performance. I think basically we are done. So I hope it was entertaining. I hope you learned something. Yeah, let me know your feedback. So since we do not meet personally, I cannot read your faces. I hope it was interesting listening to me and you will continue using KLayout. So I would recommend you look into the scripting features if you are concerned with layout generation or with things like layout analysis. I'm looking forward to getting feedback and to enhance functionality and make things better in the future even. Thank you for listening.